right, so as we move to hear from our keynote speaker, his contributions and achievements to the VLSI industry are tremendous. He's been serving the VLSI industry for more than 29 years now. It is my honor to introduce our distinguished keynote speaker, Dr. Vijaykumar K, who has been with Wipro for over 24 years. He has done architecture and design of several complex cutting-edge SoCs, ASICs, FPGA, and systems in various application areas for top-notch semiconductor companies globally. And he's also specialized in video domain and created several solutions around video compression, post-processing, and deep learning, etc. He has been granted 22 US patents so far. He's currently working on the next generation architectures of semiconductor devices, including edge devices with machine learning and GenAI. So with this, please join me in welcoming Dr. Vijaykumar K.
Thank you. So good afternoon, everyone. And my name is Vijay, and I'm part of Wipro Limited. And I've been with VLSI Group of Wipro Limited for 24 plus years now. I've been working on various SoC architectures and system on chip for various applications like automotive, consumer, medical, IoT devices, AI/ML devices, and so on. So today we'll talk about what is the impact. You might have heard about a lot of GenAI. AI has been there for quite some time. Now everybody started talking about GenAI, generative AI. What is the impact of that on IC design is what we'll look at it today. Before we go there, I just wanted to introduce our group a little bit. Quickly about Wipro, VLSI Group. We have been designing silicon for last 30 plus years, in which I have seen 25 myself, been there with Wipro. So we have done silicon designs all the way up to 5 nanometer, taped out in production. And today we are working on 3 nanometer designs, 3, and upcoming 2. So as you can see, really we are at a place where it is cutting edge. And we have actually done tape out of at least around 250 silicon devices in last 5 years, which is about 50 per annum. That's a big number. And top 8 out of the 10 global semiconductor companies are our customers. And we do real end-to-end. It's not like we give pointed services like design, verification, no. We do spec to GDS2 and beyond. Post-silicon validation, pre-silicon validation, plus microarchitecture development, RTL, DV, DFT, physical design, tape out, embedded software, which goes along with it, plus the system design, which goes along with it. The actual product. And for some customers, we have taken even up to production ramp. That means we understand test and product engineering, which includes ATA test, characterization, qualification, production ramp, yield improvement, everything. And then we work with several customers, hyperscaler companies, and then semiconductor companies one side, hyperscaler companies other side, and then also startup companies in a third dimension, mainly on the AML side, on the hyperscaler side. So today I'm going to talk to all of you mainly about GenAI with my experience of designing chipsets for customers in AML space. There's a lot of buzzwords, AI, ML, DL, GenAI. We will see today what is all about. Where are we going actually, right? So we look at that. And we have also done some chipsets for AR, VR. Okay? So we work with almost all the foundries, TSMC, Global Foundry, UMC, and Intel Foundry as well. And we have done about 500 system designs in last 10 years. So that's the kind of volumes we have. 250 tape outs in last 5 years, 500 systems in last 10 years. So that's our portfolio of the experiences. We are about 3,500 engineers for silicon, embedded software, and system design. That said, what did we do on AI space as Wipro, as a company? Not just VLSI. We'll go into the VLSI very quickly. First 2 slides, I'll keep it to Wipro, then I'll get into actual AI space. So what did we do? Wipro has committed to invest $1 billion into the AI space. We have developed a platform called AI 360. This is a major platform which goes to the enterprise applications predominantly, like you can say smart enterprises, and then many, many applications like AI for IT. IT, when I say IT includes, this is like a overall company-wide, that's why we call it as IT, but then you see here there are edge devices and robotics and all that comes into picture. So basically, this is a platform which we offer to the customers with which they can build various applications, either real-time applications, it could be enterprise applications, it could be HR applications, many, many use cases for banking, insurance, healthcare, medical, and then also VLSI, chip design space also, this platform can be used. So this is a platform which we have developed over a period of few years, and we are heavily investing further on that. So with that, first let us try to resolve this issue. I think a lot of people talk about AI, ML, DL interchangeably, and GenAI is now. Why? What is the difference here? Actually, nothing new. If you have to look at AI really, it goes back to 1950s, where actually the AI come into picture. But it didn't pick up at that point because the compute was the limitation, number one. Data availability is the second limitation, but compute was the primary limitation. But today we don't have that limitation. 10, 15 years ago, we have done something called ML, machine learning, 10, 15 years ago, actively. At that point, what we did, we have to do an object detection. We can do it using features like, manually one has to define what features to look for in the image. And then you would say whether it is a face or whether it is something else. Very painful exercise. 10, 15 years ago, maybe 20 years ago, that is how it was. Thanks to the neural networks, when neural networks came into picture, at that time, feature extraction started to happen automatically. That is what we started to call it as a deep learning. Okay, with deep learning, we can do object detection, image classification, non-imaging data classification. All this can be done, automated way. Okay, feature extraction. There's no need to extract the features manually, which we used to do 10, 15 years ago. So now GenAI, what is this GenAI? Now it's generative AI. Extension of, it's all, if you look at it, all of these are subsets of each other, right? So GenAI is the lowest level subset. Basically, it can generate the code, text, images, with a given description at a very high level. But what is the impact of this on VLSI? We'll come to that point. But everyone, like deep learning has its own impact, and GenAI has its own impact. And today's main discussion will be on this GenAI impact, which is upcoming now. It's being talked about now. It's already there. What is the impact, and how does it matter for us as a semiconductor engineers? We should know that. That's where the point of discussion will be here today. So before we go to get into the actual details, if you see the landscape, GenAI, it is anticipated that today, last year's spend was around 140 millions globally on GenAI. So if you're thinking GenAI is yet to come, no, it's already there. So we see that we already spent 140 million, and it is expected to grow to 1.7 billion by 2033. That is the rapid phase. It is going at a CAGR of 29%, where the semiconductor industry typically is at 6 to 7% or 8%. So you can see the rapid growth. Now, why is this growth happening? We'll see it shortly. And where it applies, and how does it matter for us? Is it optional or is it a mandatory? Do we need to know, all of us need to know that? How does it impact the VLSI industry per se overall? So first of all, what is the need? Why GenAI? What is it for? So as you know, chip complexities are exponentially growing. We can't do a lot of things manually. It takes time which is unproportional, which we can't afford to do it. So there's something which we are pushed to the wall. One side, complexities are going up. Second side, your time to market. You need it faster. You need the tape out in 6 months, 9 months. So one side we are pushed on that. Third way, also design productivity. What is the productivity? How fast we can do? How to improve efficiency. All these are being pushed. Now, how GenAI will help? Please hold on to the minute. We'll come back to that. There are some issues also with GenAI. We will talk about all these things in detail. But this is just to show you there is an immense potential, as you can see here, with a growth rate of 29% in next 10 years. So if you're thinking it is going to be there or not there, it's clear. It is going to be there. So now, last year, 2023, we spent about 140 million, I said, globally on GenAI. Now, where this has been spent, if you look at in various VLSI functions, this is the digital logic, this is physical design, analog mixed signal, power optimizations, design verification, other applications. Very interestingly, most of the money on GenAI side was spent on design, actual design, which means microarchitecture assessment, trade-off analysis, PPA analysis, all those places where it's being spent now. And going forward, it will be much more here, design verification. I think, in my opinion, next 5 years, we will see a lot more design automation done for debug. It's going to revolutionize the verification aspects. I myself have seen a lot of demos because we have been working on. You just give the test cases, log files, VCD files, FSDBs, everything, and it is showing this is a transaction at which there is an issue. Otherwise, manually, I would go and pull signals and then look at all the things, which is, you can imagine the productivity improvements it can do. And so as there is a big play on the physical design space also. So going forward, continuing to be there on the design side, you will see a lot more on the physical design side, on the design verification side. Plus, last but not the least, it has a major impact on the ATPG. If you're aware of the DFT type of story, there a tester time matters. So how much time is taken to test on the device on the tester, and how many test vectors are required, GenAI can optimize a lot more faster. We'll just come to that point. So this is just to give you an idea about where the spend happened already last year. And though we are talking about today mainly on the VLSI, it has impact on the entire plethora of things on the product engineering side. Not only the VLSI, not only hardware, GenAI has got impact on every area. You talk about 5G, you talk about Industry 4.0, you talk about automotive, embedded engineering, everywhere. Cloud, obviously cloud is a major contributor of all this training and other things happens. So now, we will actually come to the, again, trying to resolve AI, DL, GenAI, silicon. What is it all about? Where is it each function? Actually, if you really look at it, why are we going there first place? I talked about today, we are also working on 3 nanometer designs, right? So we are talking about today 3, 2, 1. It may be non-silicon material, right? So going forward, that is where we are headed. So, and then you may be surprised, but today our die size is about 500 to 600 mm square. Some of the designs we are working on, AML. 500, 600 is a limit of the manufacturability, no more. Enough, we have reached a point where we can't manufacture anymore. Now we came with the chiplet concepts. We said, okay, functional blocks, die-to-die interconnect, multiple dies, we'll stitch it, we'll make a package, fine, done. Now that called for 2.5D 3D packaging, complex packaging structures where we put multiple chiplets and then achieve a bigger space. So all these things are becoming unmanageable manually. A lot of these factors. So this is where something has to be done, more than automation. What we need is more than automation, not just automation. That is where GenAI is coming into picture. So just to be clear here, I just wanted to explain you what is a silicon area, because see, these are multiple different areas. These are interchangeably, interlinked people use, but then they are very different. If you look at here, training, all of us know AI needs a training. Training will happen on the cloud. Cloud would have CPU, GPU, TPUs and all that. So here there is a silicon space because we designed these. So you look at the impact of VLSI on the AI space, right? So we designed these chipsets. That is one area. Inferencing, as you know, inferencing happens on the edge or sometimes on the cloud. If it is happening on the edge, that could be CPU, FPGA, maybe ASIC. That is the last one, silicon. Now, first three are, we designed silicon for AI. Now, the next one, if you look at GenAI, GenAI is designing, assisting to design the silicon. There is a difference here. I hope I am clear. So first one, we designed the silicon for AI. Now GenAI is expected to assist us in doing the silicon design. That is where we graduated to. So when we talk about accelerators, when we talk about deep learning accelerators, all that comes under this category. This 10 years ago and recent past, we designed silicon. But today we expect GenAI to assist us in doing silicon design. That is a slight difference. So that's where we are today. So definitely there are multiple market segments of all these applications. So I will just skip this part. This is a very important aspect. Now coming to the Gen AI, right? So where is it the impact and how it will impact? For example, I will try to give some examples so that it will be clear. Let us talk about multiple areas, front end, back end, other areas. Front end, digital design. Now, there are many trade-offs we do, right? When we are working on microarchitecture, we say what should be the width of the bus, speed of the bus, is it the right configuration, is it the right architecture? Those trade-offs manually, if you do, or using models, it's pretty time consuming. And if there are learned models, models can perform much better. Because we have trained that model into multiple scenarios and it can extrapolate other scenarios. Now, you might have also heard about it, RTL code generation. Today, there are co-pilots, assistants which can do, but that is not enough for us. We need much more than that because we need that to be synthesizable, frequency aware, power aware. So all those things, long way to go, but one day for sure it will be there. And the code, most of the integration also will happen using these GenAI tools. That is for sure, we will see the impact. And analog design, you will see a rapid growth. Analog design, today we are struggling for node migration. Because the nodes are changing so often, we need a way to port or migrate from one node to another node. So we'll see a big impact in that area. Design verification is the biggest impact, I would say, and it needs it. Today, we do a lot of manual debug. It depends on the expertise of the engineer who is debugging it, protocol knowledge required, and you know, debugging is always an art. The point is, this tool learn the actual correct transactions. It will easily show which is outliers, and it will say, okay, this is the place you can go and look at it. And this is there today. It's already there. It's not future. We have seen the demos. We are there. So that is a major impact area we need to watchful about. And physical design, big time. Right from the floor plan, power plan, IO plan, CTS, clock routing. Okay, you talk about the area, it's a lot of manual effort is involved. Because if you get, and then physical verification, you get 100,000, 200,000 violations. Where do I go and check manually, right? So it's a time-consuming process. So these tools can streamline based on its past experiences and say, okay, now these are the group of signals to look at first. These are the paths to look at first in the timing. And while placing also manual placement, right? Today we do floor planning, we do it manually, memory is placed on. I think no big deal. The tool will be able to figure out much better way in terms of where to place based on the nets and based on the logic and so on. So all these are happening today already. There are hundreds of tapeouts happened already with using these tools. It's not that it will be future, okay? And these two areas are going to be a major impact. And other areas, test and product engineering, which is also mostly time consuming. DFT, vectors, somebody goes through these vectors, find out which vector is the right set, Do we need some other set? Or, test time is optimal because test time is money, a device cost. So that is one area we see a major impact will be there. And of course, last but not the least, all the training, others internally or wherever we train engineers, a lot of these tools will help in terms of a new engineer to understand. But one thing to understand, all these are not that GenAI will come magically replace everything. No. That's why we carefully call it as assistant or co-pilot, right? Whichever way we use. It is there to assist the engineer to do the job faster. That part need to be clear in our minds. It's not like an engineer has been replaced with the GenAI tool and it will push button and we're done. No. So what we are doing internally is that these are the solution areas. How it evolves for a company, right? So we go and look at all the tools because EDA tools are there already. We go and look at the tools. We set up the flows internally. We kind of develop some IPs and some SOCs using that flow, as opposed to manually if we were doing how it would look like. So we are doing all kind of benchmarking of that kind of data to see what real impact it has got and what capabilities it has got. And last but not the least, we say we are bringing something out of the box, right? So we are bringing some GenAI. Now, I have ASIC flows established for years. I need to see how to integrate all these things into one flow. That's another challenge which we'll get into. But having said that, we want faster development cycle. And we want efficient development cycle. We want the best die size. We want the power to be optimal. We don't want to burn any extra single microwatt extra power. And no matter whether it saves 5% die size or 10%, doesn't matter, it's a big number. And test coverage, how fast I can debug. Now, you may be surprised, but the expected PPA or productivity improvement is about 10 to 30%, depending on various tasks. On the die size, I would say 5 to 10% we can expect. And productivity as in debug time. Okay, those things we can expect up to 30% reduction in if you done it manually completely. So this is the thing what we have seen so far, and this is what our expectation is from these tools. Now, I talked about the EDA tools. All the tools are out there already in production state. All the three major EDA companies. And again, I just want to mention that it's not like a push button. As I said, it's like you need to set up the flow around that and benchmark it and then take it forward, right? So these are the tools out there, all the way from the D stands for design, verification, 3D packaging, and then test this analog, whereas Cerebrus, Allegro, even board, and IC architecture, verification, implementation, so on. All the tools are out there, but again, this is not a push button. On the right-hand side, you see what is involved really, right, around this. For most of the times, in my opinion, there is something called prompt engineering. What matters actually? See, you might have heard about LLMs. This is popularly, everybody says, large language model. That is the basis for all these things behind. So, how best data output we can get from the LLM is what is called prompt engineering. It's like, you are taught LLM with something, and then how smart you ask the question so that it gives you the result, what you expect from it. For example, one simple example I'll give you, right? So there is a 600-page manual. One has to go through to understand all the commands, to group all of them to do a certain task. Just give that manual to this LLM. It will learn from that, and it will say, okay, I want to do IO timing analysis. Give me instructions. It will give all the list of the instructions. So it is that powerful once learned. But this prompt engineering, most of our engineers going forward will be doing some sort of work around this, apart from VLSI. If you're thinking only VLSI, that's not going to be adequate anymore. So apart from VLSI, our engineers will be doing on combination of these things. Most of the times prompt engineering, that means already somebody trained the model. Okay, what kind of questions I'm going to ask to get my answer in my right way, right? And then there is something called concept called RAG. I'm not getting into that. But somebody has trained the model. I train another wrapper around that model, which will actually fine-tune that model to my requirement of my company. That's what we call RAG models. And there is fine-tuning. Somebody else has trained the model. I might have to little bit fine-tune to my specific tasks. And then pre-training, for example, I'm doing something innovative. So no model is there available in the market. I take a standard model. I completely train from grounds up. So all these areas, our VLSI engineers will get exposed to. And they will be equipped. And they should be ready to take up these aspects. So what my suggestion is that upskilling is needed, or reskilling or upskilling, whichever way we call, for the organization as well as for the individuals today. In fact, it is already late if we are not started. So definitely these areas are to be looked into, because no tool can give, it's not like I give a tool and say, this will do a floor plan. No. Floor plan depends, or LVS and DRC depends on which process node, which foundry, which design. So you need to train these models to your flow of designs. Then only it will be able to suggest you the best. Okay, now we talked about many things. We said, okay, it has got many advantages, many areas, many possibilities. Yes, but there are no challenges? No, there are many challenges. There are many, many, many challenges. Like simple things we talk about, data availability. We say we train the model, easy to say that, but it's very difficult to get the data, right amount of the data, right quality of the data. And if you don't have the right data, it can completely mislead, and you may end up spending more time in debugging the LLM model than the actual design. So we need to be a little careful about that. And sometimes it may overfit, it may underfit. That means the model may get tuned to so much. So there are a lot of complications. It's not that straightforward, or it is not that magically somebody else will give us a model which can do all our jobs. No. We need to understand those aspects critically, even though we are VLSI side. And then integration challenges. Okay, we are talking about LLM, GenAI. How do I integrate into my flows? My flows have been there 15 years, 20 years in our organization. How to integrate that? That's another challenge we are seeing already. And data leakage and security concerns, major concern actually. So what is happening is that a lot of data it needs to train. Now my data is safe or not, where this data is being used, how this data is being used, because these LLMs, unlike if you worked on deep learning, you would know, you can clearly see a text file with all the layers, but LLMs are something which are not that transparent, right? So you would not know where this data is being used, how is definitely a concern for organizations. And models are too complex. If something goes wrong, let us say if the model is showing something wrong, which is not what you expected, it's hard to debug that. So that is another challenge which we see with this kind of GenAI. And training takes humongous amount of hardware. Hundreds of GPUs it needs. Terabytes of RAM and multiple number of days for training. So this is definitely another challenge. I wouldn't say it's a major challenge. We overcome all of that, but this is still a challenge. So 2-3 takeaways. One is that GenAI is already there. It will be there, and we need to be upskilling ourselves to that, number one. Otherwise, 2-3 years down the line, our productivity will be 30-40% lesser than somebody who has adopted GenAI. Simple thing. Second thing is, it's not a push button. We need to be upskilling ourselves to these technologies, be ready for it, and start deploying it. And however, at the end, it comes with its own challenges to be aware of. So I think with that, I come to the end of my presentation.